formula. I'm going to start with my explicit formula. Whoa, that erases. That writes explicit. And my explicit formula for geometric is going to be a sub n equals my first term times our common ratio to the n minus 1. Our recursive formula is the term I want equals our common ratio times the term before it. Which just means between each term you just multiply by that number. So I don't think this is that hard to remember. Recursive should be semi-okay, because it's not really anything you have to memorize. It's just you multiply each term by r. That's why it's r times the previous term. It's our explicit that we definitely need to know. Arithmetic. Arithmetic, our explicit. Let's call it EX. Our explicit. We have two explicits. I usually stick with a sub n equals my difference times n plus c, where c is my a sub 1 minus my difference. You also can write it, if you want to, you can write it as your first term plus d times n minus 1. Either one's acceptable. This one makes your life a lot easier if you know this one, because you skip right to the explicit that you'd probably want for sum and stuff. So I would know this one, it's quicker. Alright, then my recursive. Well, that's just the term I want equals the term before it plus whatever our difference is. Right? Because we just add, and add. So those are our 4 formulas. Alright, we need to know those. Remember, next Wednesday is going to be our test. I'll alternate some stuff because on Friday I think a big chunk of students are going to be missing for a macro or micro test. I keep forgetting which one it is. Which one is it? Micro. Yeah, I'm assuming several of you were in it because you all repeated micro. Alright, so we might alternate some stuff, but we'll still have that test on Wednesday. We might just alternate what we're learning on given days. Okay? We'll still have a test on Wednesday. Alright, the first thing I want to start off with is questions from the homework. Yeah. Number 70. Is it a hard one? Let's not do the hard ones. It's the senior's last day. Can't we just avoid the...
We should play again.
Right?
Right.
Alright, number 70. We're supposed to write this in summation notation. And we know it's a geometric sequence. So the only thing difference between here and here is I multiply by b here. Which means we're 70, right? Am I on the right one? Yeah. Okay, sorry. You looked angry at me for a second. Alright, so to get from a to a times b, I just multiply by b. To get to the next step, I multiply by b. I'm going to multiply by b, I'm multiply by b, multiply by b. So my r value equals b. My very first value is just a. Now I just got to figure out how many terms I have. Well, b to the first is my second term, right? I have a and then b to the first. That's 2 terms. So 1 is my 2 terms. Let's see how we say this right. So 37 must be 37 plus 1 additional term. So we actually have 38 terms. Did that make sense? Why we have 38 terms? So our n equals 38. So that means in summation formation, we'll have I equals uno all the way to 38. And my explicit form of a geometric sequence is my first term, which is a, times my r value, which is b, to the n minus 1. Do all those steps make sense? If you could see them? Sorry, it's a little low. Alright, so the whole point was just recognizing that we multiply by b. That was the big trick to that question. Alright, other questions? Jeffrey? 59? 59, we're supposed to find the sum of each finite geometric sequence using the formula S sub n. So we're multiplying by 2, right? Negative 2. We're multiplying by negative 2, so that's my R value. My very first value, A sub 1, equals 1.5. And how many terms do I have? I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 terms, so my N equals 8. So my S sub 8 is going to equal my first term, 1.5, times 1 minus R, which is negative 2, to the 8th. And it's all over 1 minus our R value, which if you plug in should come out to your answer. I forget what it is. Does that make sense?
Yeah.
All right, so we just got to find those 3 things and you can find your finite sum. Other questions? Yeah?
For 79,
Let me get to it. Yeah.
so if the difference is 1 or greater, you can't find the sum for a final solution, but
Cor-
if it's on the negative side, is that the same thing?
Remember what it was? It was absolute value of R has to be less than 1.
Oh, so you can't do 79?
So you cannot do 79. You cannot find the sum. Because the absolute value of negative 1.6 is going to be a positive 1.6, which is greater. So you cannot do 79. Well, you can. You can just say that you can't find the sum. Yeah, Jeffrey.
81.
Say that one more time.
81.
81. 81, we're supposed to find the infinite sum of that. Can we? Yeah, because our R is definitely less than 0.1. So our R is less than 0.1. So we get our value is 0.1. Our A sub 1 equals 6. So our infinite sum, S sub infinity, is going to equal our first term over 1 minus 0.1. And whatever that comes out to is going to be our sum. Because that's our formula. Remember, our anytime it's infinity, either we can't do it, or it's A sub 1 over 1 minus R.
Yeah, so the answer in the book says it's 2/3, but I got 6.66.
Say that again?
In the book it says 2/3.
It says 2/3.
In the book they did 0.6 over 0.9. So, is that just a mistake?
Probably. I'd have to look at it. I'd have to look at it. Yeah.
Your first term is 0.6, not 6.
Oh, yeah. Thank you. Thank you for pointing that out. Yeah, because that could not be, the total seemed really high. My A sub 1 is not 6. Thank you for pointing that out. It is actually, because we didn't start at 0, this one's set up a little bit differently. It is 0.1 to the first, which is going to equal 0.6. So this is 0.6. Thank you. I think I would have got there, it was just because that sum did not seem right as soon as you said 2/3. Like it should have been 2/3. Thank you. Otherwise, I would have been pulling my hair out for a second. There. Now I feel better about that one. Okay, other questions? Okay, cool. Then we'll start today's lesson. Today's lesson is on permutations, for the most part, and the fundamental counting theorem. Let me get to it. Where are you? Where are you, guy? I know you're here. Oh, you will not send the project, will you? Okay, there we go. All right, the fundamental counting theorem, and it's based on this, what we're going to cover first. So consider it 6 a.m. You're groggy, but you have to pick out an outfit to wear. Lucky for you, you didn't do laundry, so you don't have many options. You have, hey, I'm going to go ahead and change 3 pairs of pants to just 2 pairs of pants. I'm going to change that to 2, just so we can delineate between the 2 and the 3. Oh, now you have to refine your choices to 2 pairs of pants. And 3 t-shirts to choose from. How many outfits can you wear? I think we've seen these problems plenty of times. I'm just going to go over a couple bits of information because this one isn't hard. Other ones can be more difficult. So there's one way we can solve this, so we can do a tree diagram. And a tree diagram just has you sitting here, picking out clothes in the morning. And we're going to pick our pants first, either pant A or pant B. Here you can either draw pictures or just write the words. I'm going to probably write the words because I don't have much room to do a great drawing. So we have two choices. We have pants number 1. Oh, let's make it more fun. Let's say we have red pants. And what's the other color of our pants? What? Blue? Orange, you glad I didn't say banana? So I have blue pants. And now we have 3 shirts. So if I pick my red pants, I have 3 shirts I can wear. I'm just going to call them shirt 1, shirt 2, and shirt 3 just to save some time. Shirt 1, shirt 2, shirt 3. And we have the same choices with our blue pants, assuming everything matches and we're not freaking out about that. So I have shirt 1, shirt 2, and shirt 3. So if I pick red pants, I have 3 choices of shirts. So these are all 3 outfits I can wear with red pants. If I grab blue pants, I have 3 more outfits I could wear. So I have a total of 6 outfits I can pick from. So I have a total of 6 outfits. Well, that leads us to that bottom notice. So it says, notice that each choice of pants leads to 3 choices of shirts. In other words, I have 2 choices to begin with times 3 additional choices. So now if I added shoes in the mix, I would just multiply by how many pairs of shoes I have, multiplied by how many bracelets I could accessorize with, multiplied by how many hats I could have, multiply it by, what else do we wear? Socks. Oh, we need socks. We need socks multiplied by socks. So we're just going to take each item and multiply how many choices I have. And in this case, it's just 2 times 3, which comes out to 6 outfits. All right, so if I have 2 items to choose from, and I have multiple of each, then we just multiply them together. And that is our fundamental, well, it's right up there, fundamental counting theorem. We're going to put that right here. So this is the fundamental counting theorem. Notice that each choice is kind of independent of the other one, right? Pants don't affect shirts. All right, I have 2 pants, so you stick with 2 choices. I have 3 shirts that are independent of each other. So if you can choose one item from group M and a second item from group N items, then the total number of 2 item choices is M times N. So like that says, and be careful about this because we're getting more complicated stuff. If you're just choosing one item from group 1, an item from group 2, then your total choice is how many items you have in group 1 times your items in group 2. And that can expand to group 3. Like I said, we can add socks in there, we can add shoes in there, we can add any kind of accessory in there. We're just choosing one of each item. So be careful when you're using this law because we're going to get into permutations which are a little bit different. So my example here is a phone number is composed of 10 digits. The first 3 are the area code, which cannot start with 1 or 0. All right. And the other 7 are your local telephone numbers, which cannot start with 0. And my question is, how many possible phone numbers are there? Just set this one up. See if you can set this one up. See if you can set up, maybe don't solve it just in case you're wrong. How many choices do I have for my very first digit if it can't be 1 or 0? Yeah.
Would be 8.
I would have 8 choices. Well, I have no restrictions on this next 2, so you have 10 choices. It can be 0 through 9, right? Because you can't have 10 as a digit. You can't have 8, 10, 10, 11. So we have 0 through 9, so you have 10 choices here. I have 10 choices here. The other one I have a restriction on is this one. This one can't be 0. So we have 9 choices. We have 9 choices here, and we have 10 choices for all of the rest of them. So now, according to the fundamental counting theorem, since I'm choosing one from each group, I just have to do 8 times 10 times 10 times 9 times 10 times 10 times 10 times 10 times 10 times 10. So we're going to multiply them all together. And once we multiply them all together, so we're going to multiply, maybe I'll put that down here. Multiply. And we're going to come up with, ooh, I didn't leave myself much room, but we're going to have 7,200,000,000 possible phone numbers. And right now we don't even take up half of those. So we have plenty of numbers to go around still. There was a concern at one point that we were running out of phone numbers because they thought the population was going to keep growing. But then you realize that, hey, when people die, they get rid of their phone numbers. And so it fluctuates up and down. And they don't even project till I don't know, even 2200 will still have enough phone numbers to go around. So don't worry about losing your phone number. So that's a really big number of combinations we could come up with. If we ran out of phone numbers, they would just add a new digit. Right? You just put a 1 in front of there. Okay, so that is our fundamental counting theorem. The next thing we're going to do now is called permutations. So let's say you're giving a speech on books. And you want to start with some jokes. Here are 4 jokes you can tell. So you have 4 jokes. I don't know why you're telling a whole bunch of jokes all at once, just start off with. But we have 4 jokes. I like to play chess with old men in the park, although it's hard to find 32 of them. Get it? Get it? Because they're your chess pieces.
I gotta lose this.
Our next joke is, if a word in a dictionary is misspelled, how do you even know? Think about it. Maybe something's misspelled and we don't know. A bit of advice, never read a pop-up book about giraffes. And a few decades ago, we had Johnny Cash, Bob Hope, and Steve Jobs. Now we have no cash, no hope, and no jobs. Please don't let Kevin Bacon die.
Funny, Bacon's already dead.
So the question is, how many different ways are there to tell these joke combinations if I'm telling all 4 of them? So let's start with joke number 1, my very first joke. How many jokes do I have to choose from for my joke number 1? Thanks, Mike. 4. I got 4. I have 4 jokes. So I told joke number 1, and now I'm telling joke number 2. Although I don't know which joke I picked, how many jokes do I have left to have for joke number 2?
3.
I have 3 left. I have 3 left. And now if I tell my 3rd joke, following that sequence, I only have 2 jokes to tell left. And finally, my joke number 4, I'm down to my last joke. So using the fundamental counting theorem, we're just going to multiply these guys together. We're going to say I have 4 choices in the beginning, 3, 2, 1. So this actually equals 4 factorial, which is 4 times 3, which is 12, times 2 is 24. So I have 24 different ways I can tell these jokes. The big thing is, does order matter? You sure? I think order matters a lot. Because if I say this is my first joke and I tell it last, did I follow my... So if I set this up for Sarah to tell, and I say tell this joke first, you have to tell this joke first, and she tells it last. She didn't follow my directions, right? So order definitely matters in this one. All right, so order matters. Which joke is first, second, and third. You can delineate between which one. So order matters in this one. And that gets us to something called permutations. So a permutation is an ordered arrangement of items that occur when no item is used more than once. So as soon as I use a joke, it's gone. I can't use it anymore. And the order of the arrangement makes a difference. The order in which these jokes are told makes a difference in terms of how they're received. Because I'm picking the order to make the most effective speech. Although all 4 jokes would be kind of ridiculous for a speech. But all right, then we have some notation. So permutation of n things taken r at a time. The notation p of n of r represents the number of permutations if r items are taken from n items. So in that jokes one, let's go back to that jokes one. I had 4 items, and I actually chose all 4 of them. So in this case, it'd be p of 4, choose 4. All right. However, if I only chose 3 jokes, if I only chose, let's say we only chose 2 jokes, I would have just had 4 times 3, so it would change by how many jokes I'm going to tell. So that's where the number of items is going to be important. We have to know how many total items we have and how many items we're going to choose from. It'll make more sense in the next problem. Okay, so we're going to do our next problem. So you are a coach of a Little League baseball team with 13 players. You need to choose a batting order having 9 players. So obviously the order matters. Because in baseball you want your strongest batter either third or first. And it matters what order they are because it might depend on what position they play. So order matters. So because order matters, order makes a difference, that automatically makes it a permutation. So we have 13 total players to choose from. We have 13 total players to choose from. So that's going to be our n value. It's our starting value. That's how many, the pool of stuff I have to choose from. Like our jokes, we have 4 jokes to choose from, so our n is 4. I have 13 players to choose from, so my n is going to be 13. Well, all 13 players can't bat in that 9 spots. So that leaves us with our R value. Our R value is how many I'm picking. And I'm picking 9. So the notation of this one would be a permutation, 13. So permutation of 13, pick 9. So I have 13 pool, I'm picking 9. Then we just plug it in that formula. Well, that formula tells me we're just going to have n factorial over n minus r factorial. So we do how many we have over 13 minus 9 factorial, which is going to equal 13 factorial over 4 factorial. I want to note something really quick, because you can definitely plug this in your calculator. You can do 13 factorial times 4 factorial. And like I said, it's in your math. Check on your math button. If you have your calculator, go to your math button and go to your probability, so it'll say PRB. You'll see that there is an exclamation point there. Did we find it? So all you have to do is 13, that, divided by 4 times your factorial button, and you will come up with your answer. I do want to go over this a little more in depth, though. It doesn't work out well for this one, but sometimes you can do these in your head, because this would be 13 times 12 times 11 times, and we repeat that until we get to 4 times 3 times 2 times 1. And that's all over 4 factorial, which is 4 times 3 times 2 times 1. Note that these things cancel out. So in fact, if you're doing this division and you just want to type this quickly in your calculator and you can't find your factorial button, you just have to do 13 times 12 times 11 times 10 times 8 times 7 times 6 times 5, and you don't do any further because 4 factorial gets rid of the rest. So in fact, this is just 13 multiplied all the way till you get to 5. But no matter how you solve it, you're going to come out to $259,459,200 different ways you can make your arrangement. Okay, our last one. If 4 officers are elected from a group of 12 and no person can hold more than one office, how many different outcomes exist? Your first question is going to be, and you'll know why tomorrow, does order matter? So I'm picking office. So we have president, vice president, secretary, and treasurer. Does it matter which one you get? Are you equally as happy with president as you are treasurer? Maybe, but do they hold different offices? So does the order matter of how you get picked? Yeah, the order definitely matters. Order matters. Order matters because you could think of your positions as president, vice president, and so on. So order matters, so it means it's a permutation. Oh, got away from me. Permutation. So I need to find how many items I have to pick from. Well, we have 12 people in the group. So our total number of people we have are 12. And we're picking 4 officers. So that makes our R equal 4. So that means our permutation notation is going to be P, start with 12. Pick 4 is going to equal the total number I can pick from over the total number I can pick from minus how many I'm picking, which is going to be 12 factorial times 8 factorial, which actually just equals 12 times 11 times 10 times 9, because your 8 factorial will cross out from the top and bottom. This is the one that's nice and easy in case you can't find your factorial button or you just have a 4 function calculator, because now you can just do 12 times 11 times 10 times 9, which comes out to 11,850 different ways. Alright, so the 2 things we covered today. We first did the fundamental counting theorem, which is if you have a group of items and you're picking 1, and you have another group of items where you're picking 1, and another group of items that you're picking 1, you can multiply those choices together to come up with how many possible choices you have. On the flip side of it, we had permutations. Permutations allow you to pick more than one item per group. So these are going to be the ones that if you have a group of something, you're picking this many from. But be careful, because you have to recognize order matters. Order matters with permutations. It's going to be a big deal tomorrow that we recognize whether order matters or not. All right, any questions about what we covered today? Okay.